What we spent the last two classes doing was reviewing, or being introduced to and then reviewing, some basic numerical integration techniques, all motivated by the idea of the area under a graph. So we want to find the actual area under some graph from A to B, and we know the math thing for that is the integral A to B of f of x dx. But if we have a curved function, the whole invention of calculus was predicated on the fact that area under curves are actually pretty complicated to figure out. So we had to wait till Leibniz and Newton figured all this stuff out for integral calculus, and eventually lent us this idea of antiderivatives and all the mechanics that go with that. But if we don't have a function, or we have a function that's too complicated to take the antiderivative of, or doesn't have an antiderivative, then we resort to, or we can resort back to the idea of the area. And so the area under a curve is pretty similar to the area represented by a bunch of rectangles. And that's what we called an order zero method, which was the left-hand rule. Or the right-hand rule would be about the same. We also saw a slightly more advanced version than that, where instead of pretending things were horizontal on each interval, that they were straight line segments. Trapezoidal rule. How about the one where we fit a quadratic on pairs of intervals altogether? Simpsons. Far from uniform. Okay. In terms of expectations, you will be expected at some point to program either trapezoidal or Simpson's rule in a test. It's pretty much a guarantee. Test or the final exam. Again, we'll look at the code for that today, just to remind you how it gets built. It's a very simple idea, but you have to get the mechanics right, as always, with the syntax. But that would be the expectation, is that from scratch you could write both of those functions. Out of the three, I make you do trapezoidal just because it's a nice contrast, so you don't memorize just one piece of code, but you try to look for the general themes. Simpson's, by far, though, was the most efficient of these techniques. So the question is, are we done? Have we solved integration in MATLAB? We just use Simpson's rule on everything and see what happens. Well, unfortunately not. There are some cases that get a little hairier, and we're going to see what kind of conditions bring those up. Let me just run one thing from last class, W7-2. So here we had a fairly straightforward function. It was nice and smooth. It was a temperature gradient that started at high temperatures and then cooled down, very much like the one I just drew in the diagram. And when we evaluated the integral of that nice smooth function with 100 intervals, the error for Simpson's rule was ridiculously small to start with, like 8. It's accurate to 8 digits right off the bat. And remember, when we doubled things, doubled the number of intervals, did twice as much work, we saw this fantastic improvement even, that every time we double the number of intervals, Simpson's rule, the error goes down by a factor of 16. We divide by 16. The other guys, it's 2 or 4 for left-hand rule and trapezoid rule. But they all get better. It's just a question of how quickly they get better. Now we're going to look at a different type of function, this guy right here. If you look at forcing functions in engineering, this kind of thing happens not too unrarely. It happens fairly frequently. That's a better way to say it. Fairly frequently. And where you have jumps and you have cusps, and right, the integral's fine. The integral's still a nice thing to define. It's the area under the graph. Here we're going to do up to almost 3 full cycles here. Actually, just 3 full cycles. If I gave you the formulas for these different parts of the curve, this part here is a quadratic, that's a straight line, and then it stops, and then a quadratic. And you can do that. You can do the calculations mechanically, and it will give you the exact answer that the area under that curve is exactly 23.00000. The area. So we would expect, with our fancy Simpson's rule, that we should get the same kind of performance on this kind of, it's a function, we're integrating it, Simpson's rule works great. Trapezoid will work almost as well, that kind of thing. We're going to try that out and see how it plays out in practice. So we're going to need 2 files. We're going to need the sawtooth function, which will be, I'll show you that here. The sawtooth function is, blah, 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 blah. Anyway, there's a little bit of fancy stuff going on here, but stuff you've seen before. The idea is we're going to take an interval from 0 to 4, and that third line I've highlighted there says find all the values that are less than 2. So between 0 and 2, take those and make them into r squared, basically. So we're going to have just a parabola going up, and then there's a straight line that's 4 minus 1.5 times r minus 2. That's a straight line. We've got a quadratic. That's the first part. That's the blue line, and then a straight line. And all that little modulo does is says if the number's between 4 and 8, bring it back to 0 to 4. If the number's between 9 and 12, bring it back to 0 and 4. So make everything between 0 and 4 by subtracting enough 4s to make that happen. I'm not expecting you to be able to write that off the bat, but you should at least be familiar with some of the pieces that are in there. There's nothing new except for the modulus in there. So that's our function. And again, it's a mathematical function. If I plug an x in, I get a y value back, and we can show that in the plot. So if we go to the plot, that's in W73 here, we're going to generate some linearly spaced data from 0 to 12 with lots and lots and lots of points. We're going to run those values into the sawtooth function, get some y's, and then we're going to plot it. And we'll see how that works. Run. And there we go. So by plugging in the numbers from 0 to 12, we get this graph. And it's fantastic. What we can then do is borrow from our last example, and this is why we like to modularize things. W72 had these great, this whole thing here actually is identical. We defined our function for that problem, and then we did 3 kinds of integration. Here we defined our function, and we're going to run 3 different kinds of integration on it and see how it performs. We also have exact value as the name of the right answer, which ends up being 23. So we're going to just try this. We'll clear the screen and see what kind of performance we get. And because there's this long, drawn-out build-up, you can expect it's going to be somehow different. I'm just going to comment out the plot. We've seen the plot. But I'll do the same thing we did last time, which is go up by factors of 2 here every time. Fascinating. Cut and paste error is what it is. I can tell you what that is. If you look at the integral, we're integrating f from where to where? 0 to L. This graph that we just looked at, which is still up on the screen here somewhere, where do we want to integrate it from? 0 to? We want to integrate to 12. L came from our previous code. That was like a 0.25 meter, 25 centimeter long thing. So the problem is we're integrating the wrong amount. So we can either change what L is, or we can just manually insert a 12 here, and life should get a little bit better. So notice we were close to negative 23. Well, that's sort of because we're off by 23 from the number 23. Not a huge shock that we're totally off when we had the wrong interval of integration. That's better. Those numbers are reasonable. First off, if we look at our errors, are they as good as they were before with the nice function we had for temperature? Yes or no? As good as? Yes or no? No. Right. We had 8 zeros before the decimal, or after the decimal, before we had our first error for Simpson's rule before. Now it's meh. It's like it's not bad, but it's not great. And secondarily, what do we notice? Well, last time we used to get this 1/16th bonus. If I doubled the work, I got 1/16th the error. Now we're down to half. It's actually kind of freaky how pure it is. I get half the error. I do twice the work, I get half the error. And so we have a real problem here that our performance has dropped dramatically. We don't get as good, as small an error as we did before. And when we're doing more work, we're basically what I complained about with left-hand rule, which was we only got half the error for twice the work, which is a lousy level of improvement. And this will be true for any cubic, 4th order, 5th order method. So this is a problem with what we're doing fundamentally, not with the specific Simpson's rule versus trapezoidal rule.